Engineering School Physics. Superconductivity. Engineering School Physics Superconductivity. Topic covered. In this video are, as per requirement of B.Tech Physics includes Introduction, Experimental Survey, Meissner Effect, London Equation, Hard and Soft Superconductors, Element of BCS Theory. In short, we tell you the superconductivity, in which electrical resistivity drops to zero, was discovered in 1911 by Kammerlingh Onnes, Meissner and Ochsenfeld. In 1933, showed that magnetic field B are pushed out in a superconductor. It is the basic principle of magnetic levitation using superconductors. A strong magnetic field can destroy its superconductivity. Critical current is the maximum current which can be passed. In 1986, it was reported that possible superconductivity at about 35 kelvins. It is a beginning of high-temperature superconductor and possible applications, including the electromagnets, supercomputers, and magnetically levitating the world's fastest trains. 3 times Nobel Prize for Physics went to superconductivity. The superconductivity. The superconductivity is a phenomenon in which electrical resistivity of some metals and alloys drops suddenly to zero when the specimen is cooled to a sufficiently low temperature, 1 to 10 Kelvin, the temperature of liquid helium. First, understand the low temperature we are talking about. On the temperature scale of Kelvin, 0 K is the lowest temperature predicted. Theoretically, on this scale of temperature, the room temperature is considered as 300 Kelvin or 27 degrees Celsius. Kelvin scale of temperature is same as centigrade, but starts at minus 273 degrees Celsius, 0 K. So the water freezes at 273 Kelvin and boils at 373 Kelvin. To give you the idea of low temperature available in the laboratory is by refrigeration. But below 120 Kelvin, it is called cryogenic, which is achieved at the boiling points of the gases. That is of liquid nitrogen at 77 Kelvin, liquid air, liquid oxygen, and lowest is liquid helium, 4 Kelvin. This table shows some of the boiling temperature of gases. Just to remind you, dry ice or solid carbon dioxide temperature is relatively high at 195 Kelvin. Electrical resistivity and conductivity. Just to remind you, electrical resistivity is a fundamental specific property of a material that measures how strongly it resists electric current. A low resistivity indicates a material that readily allows electric current. Electrical conductivity is the reciprocal of electrical resistivity. Low resistivity means high conductivity. of a material which is known as a good conductor. Resistivity is commonly represented by the Greek letter ρ. Electrical conductivity is by the Greek letter sigma. Resistivity, ρ, is the inverse of conductivity. ρ equals 1 divided by sigma. The SI unit of electrical resistivity is the ohm meter, and that of electric conductivity is Siemens per meter, or more commonly, millisiemens per meter. The units of conductivity are sometimes given as mhos per meter or millimhos a meter. In 1904, Kammerlingh Onnes established a cryogenics laboratory where he investigated how materials behave when cooled to nearly absolute 0 Kelvin. In 1908, he became the first to liquefy helium, cooling it to near 1.5 Kelvin. At the time, the coldest temperature achieved on Earth. After achieving the temperature of liquid helium, in 1911, Kammerlingh Onnes investigated the electric resistance of metal at very low temperature, which were expectedly going down with the temperature. In case of resistance of solid mercury, the resistance has gone down too low to be measured, which fell sharply at 4 Kelvin. Onnes recognized that below 4 Kelvin, mercury passes in to a new state with different electric properties, and this state is called superconducting state. For this research, he was awarded the Nobel Prize in 1913. The citation reads, "Using liquid helium to investigate the electrical conductivity of solid mercury, he found in 1911 that at 4.2 K, its electrical resistance vanishes, thus discovering superconductivity." Visualize his observation here. Resistance in ohms of a specimen of mercury versus absolute temperature. This plot by Kammerlingh Onnes marked the discovery of superconductivity. Thus the phenomenon in which the electrical resistance of many metals or alloys drops suddenly to 0 when it is cooled to a very low temperature is called superconductivity, and the material is called superconductors. The temperature at which the specimen undergoes a phase transition from a state of normal resistance to a superconducting state, that is, disappearance of resistance, is called superconducting transition temperature, or critical temperature, and denoted by T subscript C. This is how we describe normal conductors or non-superconducting metals and superconductors pictorially. Superconductivity has been observed in number of metals, alloys and compounds. But the practical problem of superconductivity was to operate it at a very low temperature. Remained in last century. It was in 1986 that K. A. Müller and J. G. Bend-Nors of IBM Zurich Research Laboratory in Switzerland reported possible superconductivity at about 35 K in a mixture of crystalline phases in lanthanum, barium, copper, and oxygen. LABACU-O system. They were awarded 1987 Nobel Prize for Physics for their discovery of high-temperature superconductors. This opened an era of high-temperature superconductivity, termed as high-temperature superconductors. High-temperature superconductors, HTS, are materials that exhibit superconductivity at temperatures above 77 K, the temperature of liquid nitrogen. Some examples include cup rates like YbCO, yttrium, barium, copper oxide, and BSCCO, bismuth, strontium, calcium, copper oxide, magnesium diboride, and iron-based superconductors. These materials are often ceramics containing elements like lanthanum, yttrium, bismuth, thallium, barium, strontium, copper, and oxygen. The big savings in the costs of these in the applications is due to the fact that liquid nitrogen, boiling point 77 K, could be used to cool them rather than liquid helium, boiling point 4.2 K. High temperature superconductor. No general criteria for determining whether a given metal should become a superconductor has been established. Number of theories have been proposed to explain the high temperature superconductivity. Surprisingly, those metals which at normal temperatures are very good conductors, like silver, Ag, gold, Au, and copper, Cu, are not superconductors and remain normal conductors down to 0.05 K, 0.35 K, and 0.05 K. Verified experimentally. High temperature superconductors, HTS. Some chemical compounds which are semiconductors at ordinary temperatures became superconducting at low temperatures. Specific examples of high-temperature superconductors. Cup rates. These are a major class of HTS materials, often containing copper oxide with other elements. Yttrium, barium, copper oxide, YbCO. A well-known cup rate superconductor with a transition temperature around 92 K. Bismuth, strontium, calcium, copper oxide, BSCO. Another cup rate with a critical temperature around 108 Kelvin, used in power cables and magnets. Lanthanum, strontium, copper oxide, LSCO. Also a cup rate used in research and electronics. This graphic picture shows The timeline discoveries of superconductor and specially high-temperature superconductor operating at liquid nitrogen temperature. Specific examples of latest discovery of high-temperature superconductors: magnesium diboride, NgB2, a relatively low-cost and abundant HTS discovered in 2001 with a critical temperature of 39 Kelvin. Iron-based superconductors, a relatively new class of HTS discovered in 2008 with high temperatures and potential for various applications. Other examples: lanthanum ceramics, lanthanum strontium ceramics, ceramics based on yttrium, lanthanum, and strontium. These are other examples of high-temperature superconducting ceramics. Nickel oxides. Certain nickel oxides also exhibit superconductivity at high temperatures. H2S gas at 200 K and compressed at 155 GPa behaved as superconductor. This graphic picture shows the timeline discoveries of superconductor and specially high-temperature superconductor operating at liquid nitrogen temperature, including discoveries of this centenary. This picture is taken from Wikipedia. Experimental survey. Why sudden loss of the resistance? Is it due to some fundamental change in the electronic and atomic structure of the metal? The experiments suggest that the superconductivity can be affected by varying 1. Temperature, 2. Magnetic field, 3. Stress, 4. Impurity, 5. Atomic structure, 6. Size, 7. Frequency of excitation of applied electric field, 8. Isotope mass. We saw that the temperature is very critical. So is the magnetic field. We will take up magnetic effects next. The experiments carried out to study can be divided in two parts. A. To test whether this change is reflected in any properties of the metal other than its resistance, and B. To test whether the change can be affected in any other way by various physical agents. Properties which do not change in superconducting transition are the X-ray diffraction pattern. Confirmed that no change of crystal lattice is noticed between above and below critical temperature Tc. No appreciable change in the reflectivity of the metal, the elastic properties, and thermal expansion. The photoelectric properties are also unchanged. Properties which change in superconducting transition are given here. The magnetic properties change in the same way as electrical properties. In the superconducting state, no magnetic flux is able to enter the metal, like diamagnetic substance, which had zero permeability. The specific heat changes discontinuously at the transition temperature. There is small change of volume at transition in the presence of the magnetic field. Properties which change in superconducting transition also include all thermoelectric effects disappear in the superconducting state. The thermal conductivity changes discontinuously when superconductivity is destroyed in magnetic field. Impurity. Addition of chemical impurities modifies nearly all the superconducting properties. Stress. The transition temperature can be changed by a stress. Properties which change in superconducting transition also include size. Reduction of the size of specimen below about 10 micron modifies the superconducting properties. Frequency. The zero resistance of superconductors is modified at very high frequency of alternating current up to 10 MHz. The resistance is still zero, but for 10 GHz there is considerable resistance. Isotope effect and electron-phonon interaction. It has been observed that the critical temperature of superconductors varies with isotopic mass. Effect of magnetic field. A sufficiently strong magnetic field, if applied to parallel to superconducting wire, it will destroy its superconductivity and restore its resistance. The threshold or critical value of the applied magnetic field for the destruction of superconductivity is denoted by HCT and is a function of the temperature. At the critical temperature, the critical magnetic field is zero. HCTC equals zero. The variation, the critical magnetic field with temperature for a typical superconductor, is shown in the following figure and can be represented by following expression. To explain you further, at normal condition, when there is no external magnetic field, we get a critical temperature for superconductor Tc. And when a strong magnetic field Hc is applied to parallel to superconducting wire, it will destroy its superconductivity. But if we cool it further, we may get again the superconducting phase. When further extra magnetic field is applied, we have to cool further the material to get the superconducting phase. The threshold or critical value of the applied magnetic field Hc for the destruction of superconductivity is a function of the temperature. the variation, the critical field, with temperature can be represented by following expression. Hc equals H0 in bracket 1 minus T square divided by Tc square bracket closed. Critical field Hc, T, versus temperature for various superconductors is shown here. Hc equals H0 in bracket 1 minus T square divided by Tc square bracket closed. And note, the Hc, T, is the magnetic field required to destroy superconductivity at temperature T. To explain you further, we take an example. A superconducting tin, Sn, has a critical temperature Tc of 3.7 K at a zero magnetic field, and critical magnetic field H0 is 0.0306 Tesla at 0 K. Find the critical magnetic field at 2 K. Using formula Hc equals H0 in bracket 1 minus T square divided by Tc square bracket closed. We calculate it, as shown here, a value of 0.217 Tesla. The Meissner effect. Meissner and Ochsenfeld in 1933 showed that if a long superconductor is cooled in a longitudinal magnetic field down to the transition temperature, then at the transition, the lines of magnetic induction are pushed out. It was over 20 years after the discovery of superconductivity that Meissner and Ochsenfeld discovered this second characteristic, that when a magnetic field is applied to a sample of tin, Sn, in the superconducting state, the applied field is excluded, so that B equals 0 throughout superconductor tin. We show you here, by a diagram, in normal metal ore, superconducting material at temperature is above critical temperature Tc. We apply longitudinal magnetic field. Now cool metal ore. Superconducting material at temperature is below or at critical temperature Tc. We apply longitudinal magnetic field. Note it. How magnetic field avoided the superconductor. Now we show you in different way. Here by a diagram. In normal metal ore, superconducting material at temperature is above critical temperature Tc. We apply longitudinal magnetic field. Under this magnetic field now we cool. Superconducting material at temperature is below or at critical temperature Tc. Note it. How magnetic field is pushed out of the superconductor. We explain it by surface currents. The Meissner effect is driven by the generation of surface currents on the superconductor's surface. These currents, generated by the superconductors' zero electrical resistance, create a magnetic field that opposes and cancels the external magnetic field within the superconductor. This means that the magnetic field strength inside the superconductor is zero. Superconductors exhibit perfect diamagnetism, meaning they are completely repelled by a magnetic field. Observation. The Meissner effect can be observed through experiments, like the magnetic levitation of a magnet above a superconductor, where the superconductor repels the magnet due to the expulsion of magnetic field. Small magnet levitating above a high-temperature superconductor cooled by liquid nitrogen. The Meissner effect is a reversible process. The Meissner effect shows that in an external applied field, a bulk superconductor behaves as if inside the specimen B equals 0. Thus from equation B equals H plus 4 pi m, or we get H equals minus 4 pi m, so that the susceptibility is chi equals m divided by H equals minus 1 or 4 pi in CGS system. And in MKS system, chi equals m divided by H equals minus 1. A negative susceptibility, that is, a superconductor exhibits perfect diamagnetism. From Maxwell's equation, dB or dt equals minus del cross E, we get dB or dt equals 0 for E equals 0, or B equals constant, which predicts that the flux through the metal cannot change on cooling. Through the transition, the Meissner effect contradicts this result and suggests that perfect diamagnetism is an essential property of superconducting state. Thus the conditions defining superconducting state are E equals 0, absence of resistivity, B equals 0, Meissner effect, that is, perfect diamagnetism, and 0 resistivity are two independent properties of superconducting state. Critical current. With zero resistance, can we pass any amount of the current? Answer is no. An electric current flowing through the superconductor produces the magnetic field. A current I flows through a superconductor ring give rise to its own surface magnetic field. B equals mu 0 I divided by 2 pi r Tesla, or Hi equals I divided by 2 pi r ampere per meter. And when Hi is above Hc, the superconductivity will disappear. The minimum current that can be passed in a sample without destroying superconductivity is called critical current, IC. If a superconductor wire of radius r carries a current I, there is A surface magnetic field, Hi equals I divided by 2 pi r. Associated with the current. If IC is the critical current, then it will produce field. Hc equals Ic divided by 2 pi r. If an additional transverse magnetic field H is applied to the wire, the condition for the transition to the normal state at the surface is the sum of the applied field H and the field due to the current Hi should be equal to the critical field Hc. Thus Hc equals Hi plus Hhi equals Hc minus H equals Ic divided by 2 pi r. Ic equals 2 pi r, Hc minus H. The critical current Ic will decrease linearly with increase of applied field until it reaches 0 at H equals Hc divided by 2. To understand, we take a practical example. Calculate the critical current and critical current density for a sample of lead of diameter 1 mm at 4.2 Kelvin. The critical temperature for lead is 7.18 K, and critical magnetic field at 0 K is 6.5 by 10 to the power of 4 amp per meter. Solution. Given T equals 4.2 K, Tc equals 7.18 K. H0 is equal to 6.5 times 10 to the power of 4 amp per meter. So from the formula Hc equals H01 minus T square divided by Tc square and critical current Ic equals 2 pi r Hc equals 134.3 A. Critical current density Jc equals Ic divided by A equals Ic divided by pi r square is equal to 1.71 times 10 to the power of 8 amp per meter square. Type 1 and Type 2 superconductors. The conditions defining superconducting state are E equals 0, that is absence of resistivity. B equals 0, that follows Meissner effect. Please note, perfect diamagnetism and zero resistivity are two independent properties of superconducting state. After the discovery of high-temperature superconductivity by John Bardeen, Leon Cooper, and John Schrieffer in 1957, in niobium germanium, it was found that superconductors can allow some magnetic field penetration under certain conditions, and they partly obey the Meissner effect. So we divide the superconductors in two types. Type 1 superconductors follow the Meissner effect perfectly, expelling all magnetic fields. Type 2 superconductors can allow some magnetic field penetration under certain conditions, particularly in a mixed state where the magnetic field can penetrate in the form of flux lines. Type 1 superconductors Type 1 superconductors follow the Meissner effect perfectly. The magnetization curve expected for a superconductor under the Meissner experiment is shown in next. Pure specimens of many materials like mercury Hg, lead Pb, zinc Zn exhibit the behavior of the material loses superconductivity abruptly, and the magnetic field above Hc penetrates fully. These are often called soft superconductors because of their tendency to give away to low magnetic fields. They are materials that show superconductivity at relatively low temperatures. Their transition temperatures are below 30 Kelvin. The graph of the intensity of magnetization, M, versus applied magnetic field, H, shown here for lead Pb. Differentiating superconducting state and normal state by a sharp vertical line at Hc. Type 2 superconductors. Type 2 superconductors are the materials which show superconductivity at temperatures above 30 Kelvin. They don't exhibit perfect diamagnetism. These are often called hard superconductors because of high critical magnetic field, which is typically greater than 1 Tesla. For applied fields below Hc, the material is diamagnetic and the flux is completely excluded. That is B equals 0. Hc1 is termed as lower critical field. At Hc1 the flux begins to penetrate the specimen, and penetration increases until Hc2 is reached, where the magnetization vanishes, and the specimen becomes normal conductor, and it is shown in next figure. The graph of the intensity of magnetization, M, versus applied magnetic field, H, in type 2 superconductors, defining 3 states: superconducting state, mixed state, and normal state. Hc2 is called the upper critical field. Between Hc1 and Hc2, the flux density B is not equals 0 and the Meissner effect is said to be incomplete. There is a gradual fall of magnetization as the field is increased. In type 2 superconductors, in the region between Hc1 and Hc2, the superconductivity is partially destroyed and is said to be the vortex or intermediate state. It is really a mixture of normal and superconducting states, called mixed state. Note here. Advantages of type 2 superconductors. They exhibit superconductivity at higher temperatures. The capacity to carry current is higher. They are useful in high-speed computing, helping in faster data transmission. Disadvantages of Type 2 superconductors. They partly obey the Meissner effect. They are sensitive to changes in temperature and magnetic field strength. There is existence of mixed state in Type 2 superconductors. Applications of superconductors. A wide range of applications of superconductors are there, including in the generation and transmission of electricity, medical diagnosis, enormously powerful electromagnets, supercomputers, and magnetically levitating for the world's fastest trains. All these applications are primarily due to their ability of superconductors to conduct electricity with zero resistance. In superconductors, below a critical temperature, we get a lot more application. Once we have high-temperature superconductors and their availability at reasonable cost. Specific applications: medical imaging. Superconducting magnets are essential in MRI machines, enabling the generation of strong magnetic fields for detailed imaging of the body. Particle accelerators. Superconducting magnets are crucial for bending and focusing beams of subatomic particles in research facilities. Power transmission. Superconducting cables can significantly reduce energy loss during power transmission, leading to more efficient grids. High-speed transportation. Maglev trains, which levitate and move via magnetic repulsion, rely on superconducting magnets for both levitation and propulsion. Quantum computing. Superconductors are used in the development of qubits, the fundamental units of information in quantum computers, enabling faster and more complex calculations. Energy storage. Superconducting energy storage devices can store and release large amounts of energy efficiently. Electric motors and generators. Superconducting materials can be used to create more efficient and powerful electric motors and generators. London equation. F. London and H. London in 1935 proposed a modification of the electrodynamic equations to explain the superconductivity. After the classical Drude model, microscopic explanation of Ohm's law failed to explain the superconductivity. According to London's theory, it was assumed that there are two types of conduction electrons in superconductors, that is, the normal electrons and superelectrons. The variation of entropy with temperature suggests that the number of normal conducting electrons decreases below transition temperature, while that the number of superconducting electrons increases. At 0 Kelvin, all electrons are superconducting, and above the transition temperatures, all the electrons are normal. Thus the total current density J consists of normal current density Jn and supercurrent Js. J equals Jn plus Js. If Ns is the number of superelectrons and Nn is normal electrons per unit volume, and Vs and Vn be the respective velocities of electrons, then J equals E times Ns times Vs plus E times Nn times Vn. If a constant electric field E is applied to the superconducting material, the superconducting electrons face no resistance. The electric field gives the electrons an acceleration. The equation of motion of superconducting electrons is m times dvs dt equals E times E. London equation. Below the transition temperature Tc, it can be assumed that the total current density is due to the superconducting electrons. Therefore, Js equals E times Ns times Vs, and dJs over dt equals E times Ns times dVs over dt. From m times d versus dt equals E times E, we get dJs over dt equals E square times Ns times E divided by m times dJs over dt. This is the basic relation describing the absence of resistance, and known as First London equation. This states that no electric field is necessary unless the current changes. Steady currents may be set up in the absence of electric field. This is the phenomenon of superconductivity. Note the difference. The equation for normal current density is Jn equals sigma Ne equals Nne square times E over m tau, which states that the electric field is necessary for a steady current. We write Maxwell's equations. Del cross E equals minus del B or del T equals minus mu 0 del H or del T. And del cross H equals Js plus del D or del T. Or del cross B equals minus mu 0 Js plus del D or del T, where Js is the current density of superconducting electrons. Further, unless the fields are varying very rapidly with time, the displacement current density del D or del T is negligible in comparison with Js. Thus inside the superconductors, Maxwell's equations are del cross E equals minus del B del T, or del cross B equals minus mu 0 Js. Putting the value of E from dJs dt equals E square ns times E divided by m into del cross E equals minus del B del T, we get del cross dJs dt m divided by E square ns equals minus del B del T. Integrating with time, del cross Js equals E square ns divided by m times B minus B0, where B0 is the constant of integration, as Meissner effect prohibits magnetic fields. In the superconductors, the constant of B0 must be 0. Thus, del cross Js equals E square ns divided by m times B. This is second London equation. London equations explain Meissner effect. From Maxwell's equations, del cross B equals mu 0 Js. Taking of curl of both side, del cross B equals mu 0 del cross Js. We know nabla times del cross B equals del dot B minus del square B. And here, del dot B equals 0. Therefore del cross B equals minus del square B. And del square B equals mu 0 del cross Js. Using second London equation, dJs dt equals E square ns divided by m times B, and del cross E equals minus del B del T. We get del square B equals mu 0 E square ns divided by m times B, or del square B equals 1 divided by lambda square. Solving we get B equals B0 exponential minus x divided by lambda, where B0 is the flux density at the surface, and x is the distance from the surface measured into the specimen. The flux density decays exponentially in a superconductor, falling 1 divided by E of its value at the surface at distance lambda, called the London penetration depth. This solution agrees with experimental observations that the magnetic field does not drop to 0 abruptly at the surface but decays inside the superconductor through a characteristic distance lambda, called London penetration depth. Bardeen, Cooper, Schrieffer. The BCS theory. Bardeen-Cooper-Schrieffer explains superconductivity from the physics of the condensation of Cooper pairs into a boson-like state. A Cooper pair in BCS theory is a pair of electrons or other fermions bound together at low temperatures in a certain manner, first described in 1956 by American physicist Leon Cooper. The physical idea is that the first electron polarizes the medium by attracting positive ions. And these excess positive ions in turn attract the second electron with opposite spin and equal momenta, giving an effective attractive interaction between the electrons. The BCS theory explains superconductivity by describing how electrons, at low temperatures, form Cooper pairs through a phonon-mediated attractive interaction. Electrons, normally repelling each other, are attracted to form pairs at low temperatures. When an electron moves through a lattice, it distorts the lattice, creating a region of positive charge density. This distortion attracts a second electron, creating an effective attractive force between them. This attraction is mediated by the exchange of phonons, that is, lattice vibrations. When an electron moves through a lattice, it distorts the lattice, creating a vibration, or phonon, which attracts a second electron of opposite spin, creating an effective attractive force between them. Electrons in superconductor form Cooper pairs. Cooper pair is a system of two electrons having equal momenta, an opposite spin. If the attractive force is strong enough, the two electrons can overcome their Coulomb repulsion and form a Cooper pair. These Cooper pairs then condense into a single, low-energy quantum state, leading to zero electrical resistance. At low temperatures, a large number of Cooper pairs condense into a single, low-energy quantum state, leading to zero resistance. This condensation also leads to the Meissner effect, where the superconductor expels magnetic fields. In summary, the BCS theory provides a fundamental understanding of how electrons can pair up and condense into a superconducting state, explaining the key properties of these materials. Thanks for watching this video. Some more video are coming up to cover other topics of engineering school physics.